Okay. And Friday, oh yeah, the other thing about Friday, oh my gosh, I forgot. So Friday is the picnic out here, so it's almost cruel to give a test, but remember we decided that it needed to be Friday instead of Wednesday. So Friday's your test, but they're going to be having food and everything out here.
Free shirts.
What's that?
Free shirts.
Free shirts, yep.
So,
but you guys, that thing goes from 11 to 1. So if you have any time after this class, you can go out after this class. No, back-to-back classes. Another thing is sometimes my tests only take, depending upon kind of how you are, yeah, they don't take a long time, 20, 30 minutes. Sometimes they take the full time. Okay, but once you're done with the test, you're free to go. Okay, so now we need to finish chapter 3. So we talked about Copernicus, and then we talked about Tycho Brahe, and then we talked about Kepler and Kepler's 3 laws of planetary motion. Now here's the fourth guy. This is Galileo, and it's like everybody's heard of Galileo, and you might picture him with this telescope. But he did not invent the telescope, but he used the telescope to look at stars and planets and such. So Galileo was faced with, remember we're still kind of, the Copernicus revolution was the thing where basically we're going to put the sun, we're going to have the planets orbit the sun. That's the Copernicus revolution. Instead of having the planets orbit the earth and the sun orbit the earth, like what's that? So Galileo was still working with this kind of sun-centered model, and he had 3 battles to fight. And these are his 3 battles to fight. First off, people said that, oh my goodness, let's go ahead and move the sun, move this out here. This is going to be the sun. They said that if the Earth is orbiting the sun, okay, then as the Earth moves, things that aren't connected to the Earth, like are in the Earth's atmosphere, like birds and stuff like that, they're going to be left behind. So if this is the sun and I am the Earth, they said that basically as the Earth moves, birds that have left the Earth's surface are going to be left behind. Okay? It's like, oh dear, yeah. So actually, Galileo did some work with kind of what is Newton's first law of motion that basically said something in motion will stay in motion. So those birds, okay, they basically have the Earth's velocity as the Earth orbits the sun. So as they leave the Earth's surface, they are going in this direction. So they just go along for the ride. So don't worry about the birds. The other thing that he had to combat was this idea of anything that's here's the Earth. Okay, anything that's not on the Earth, that would be the Earth's atmosphere, the heavens. Okay, they are not changing. They are perfect. Okay, the heavens are perfect. Thou shalt not say the heavens change. Thou shalt not say the heavens are imperfect. And remember that Kepler actually made a breakthrough in that whole perfection thing, because he said instead of being perfect circles, he said that the planets, the Earth actually orbits the sun, not in a circle, but in an ellipse. That's his first law of motion. Okay, so Galileo made some headway there. And then the other one is that Galileo had to fight this whole parallax thing. So remember, this is where like you kind of, you close one eye and one eye at a time, and your finger, which is nearby you, looks at different positions in the background. Okay, people said that if the Earth relocates between January and July, and you look up at those stars, they're going to be kind of like slightly scrambled, okay, because you'll see parallax. So he fought that too. So like I said, he did not invent the telescope, but he used the telescope. Came in quite handy. I like to think of the first people who used the telescope were the pirates, using their telescope, yeah. Okay. So we're going to see that he used the telescope to look at things like the moon, the sun, and the planets. Quite the rush. So the first one, like I said, the whole, if the Earth moves, then if something's left the Earth's surface, like a bird or something like that, it's going to be left in the dust. Actually, he did some experiments that concluded, or to come to the same conclusion that Newton did in his first law, that said an object in motion will stay in motion, and an object at rest will stay at rest, unless acted upon by some other outside force. Okay? So he's like, say, if that bird is orbiting, basically the bird is orbiting the sun too, right? So it's going to keep that orbit. So the second thing, the whole perfection thing, okay, he actually used his telescope to see imperfections on the sun, called sunspots. Okay. He also saw that even the surface of the moon, I mean, they could see that naked eye, that when you look up at the moon, you kind of see dark regions, we call those mare. On the moon, you kind of see light regions, we call those highlands. You know, that's not perfect, okay? The other thing he saw, actually, Galileo, he didn't see it, but he pointed out the whole star blowing up, the whole nova event that Tycho Brahe saw, and like, you know, the heavens change, okay? So cut him some slack. So this was important to kind of get into kind of Kepler's first law that, you know, the orbit of the planets are ellipses, not circular. Then the third one, the whole lack of parallax, goes back to the Milky Way. Remember, the Milky Way is that kind of hazy sort of looking thing from horizon to horizon. And so when he used the telescope to look at the Milky Way, he actually could see, instead of being kind of like fog, those were individual tiny little stars that made it appear like that. So that's my reminder to you that if you're out in the evening sometime and you have either binoculars or a telescope, just look at the Milky Way and see what it looks like, okay? So the point there is that he said that, remember, parallax starts to become less and less if your object's far away. The whole thing, if you take your finger and not right in front of your nose, but if you take your finger and move it a ways away and kind of squint one eye at a time, there's less parallax. So he was saying that, yeah, let's go ahead and have the Earth relocate about the sun. The reason you don't see any parallax is because those stars are so far away. Okay, that was his point there. So other things that he saw with his telescope, he actually saw this figure right here. The circle in this drawing, this is kind of a photocopy of his lab notebook, okay, Galileo's lab notebook. These circles here are the planet Jupiter. These little things that look like stars, and they're over different nights, okay? These little things that look like stars are actually moons or satellites that orbit Jupiter, okay? So he was kind of like, you know what? If we can have a wanderer, a planet that actually has moons that orbit it, you know, we definitely can go to this sun-centered model. The other thing he said, which was even more important, was the phases of Venus. Okay, so if we're going to kind of look where Venus is, of course we have the sun, then we have Mercury, then we have Venus, then we have the Earth, then we have Mars, Jupiter, Saturn, Uranus, Neptune. So these two inner planets, Mercury and Venus, actually they go through phases. That's like the moon has phases. And this one over here, this second diagram, actually is showing you why we see phases of Venus and a sun-centered model of the universe. So over here, you put the sun in the center, okay, and then this is Venus orbiting counterclockwise, and this is Earth orbiting counterclockwise. So the thing about Venus is that actually you'll see Venus is lit up because the sun, it reflects light from the sun. The sun's light hits the surface of Venus and then it reflects it back. But right here, when Venus is right here, actually we just see a sliver or crescent of Venus. Okay? When Venus is over here at a right angle to the Earth and the sun relative to us, that actually we're going to see a quarter of Venus. Here it's going to be waxing gibbous. Here I don't think we'd see Venus, do you? Here in its full phase? Because Venus is kind of scooted around behind the sun. But notice this over here, we don't see phases of Venus. If we put, this is the geocentric, this is the Ptolemaic view. This is the geocentric model. You don't see Venus go through phases there. So that's pretty cool. So there's Galileo, and he looks kind of sad, doesn't he? Well, he had a tough life because his faith was strong in the Catholic religion, and at the time when he came forward with his ideas, his observations, the church was at a point where it said, said, no, you're going against what the Bible says. And so he died under house arrest. I think I'm thinking about that right. But he was vindicated in 1992. It's kind of interesting. Okay, so a couple other slides, just 2 more slides, and they're kind of somewhat independent topics. Scientific method of discovery, you're probably exposed to that before. So we're going to kind of either refresh your memory or kind of tell you how it works. Actually, the scientific method of learning about things or coming to the correct conclusions of how things work, it's kind of like a makes sense sort of approach. Okay, so you're probably familiar with, we see observations, okay? Based upon those observations, we develop a question. We come into a hypothesis. This is a suggestion of how things work, okay? Based upon how we think things work, as our stated hypotheses, we make predictions, and then we come up with experiments to test those predictions, okay? And there are 2 possible outcomes. One possible outcome is that your experimentation does not support what you thought it was. So then you have to either refine your hypothesis or throw the darn thing out. Okay? If you're on the right track, your predictions pass from your experimentation, then you continue to experiment. So what's not on here is a scientific theory, so we're going to add it. Actually, if you do this a lot of times, okay, you and everybody else that's in your discipline continues to try to reinforce your hypothesis, and if it checks out, then your hypothesis can be king to a scientific theory. And I like the word kinged because, like I tell students, it's kind of like if you're playing checkers and you successfully get your checker piece to your opponent's side, okay? It's hard to do, but you can. And then what they'll do is go ahead and king your checker piece. So it's kind of like being kinged. So observations, hypothesis, experimentation, okay? Any questions about that? Okay. The last slide says, what is science? Okay. So sometimes students take astronomy really thinking it's astrology. Okay, so we're not really, astrology, as some of you guys know, is your horoscope and that sort of thing. That is not a science. It fails the what is science test. So there are these kind of regions out there called pseudoscience, okay? Pseudosciences are listed down here. I mentioned astrology is not a science, okay? Ufology, although I'm just curious as heck to watch some of those videos, is not a science. Numerology, parapsychology, where these fail to be a science, even though they have OLG means the study of. They fail to be a science because you cannot thoroughly test them. You can't not make predictions and test whether you just can't. Okay. So another important aspect of not just being able to test it, but another aspect of whether it's a science or not is did it follow the KISS principle? How many in here know what KISS principle means? Okay, it means keep it simple, silly. KISS principle means keep it simple, silly. Actually, it's usually stupid, but that just seems so mean. So keep it silly, keep it simple, silly. That's what the KISS principle is. Okay, and it basically says if you come up with something that's so far-fetched, has so many complicated ins and outs of it, then you're probably on the wrong track. And that's summarized as Occam's razor. Okay. So kind of over here, ways to make sure that you're actually talking about something we generally would call science, it needs to, your hypothesis and your theory needs to rest only on natural causes, and unnatural causes, and it's not science. Okay? You need to be able to explain as simply as possible. That's why, I don't know if you remember when we looked at Ptolemy's model that kind of had those planets doing like little loop-de-loop orbits as the planets orbited the Earth. Remember, Ptolemy said that the planets orbit the Earth. That's so complicated. Those epicycles are so complicated. They kind of fail that one. And then down here, you need to be able to, whatever hypothesis or theory that you come up with needs to be testable. And those other ologies over there in my book are not really testable. Okay, very good. So any questions? Okay, so if it's okay with you,